Good morning. Today we are going to begin talking about quadratic equations, and we're going to graph parabolas today. This is a review from Algebra 1. You've already done this. I know it's been a while though, so we'll go through a refresher of it. So let's begin with the parent function y equals x squared. The reason I call that the parent function is that is the most basic quadratic equation you can come up with. What makes it quadratic is it's got an x squared. The highest exponent you see in this on your variable is an x squared, and that's as basic as it can get. So that's why we call that the parent function. And as we were talking about with transformations, you'll see different forms of that. It might get skinny or fat or get stretched or moved around or whatever, but they're all going to have the basic shape of a parabola. So here's an example of a parabola. This is the graph of the parent function, but we need to slow down and look at where that comes from again. So if you don't remember how to graph a parabola or how to graph anything at all, your basic strategy is to make an XY table. So let's start by doing that. So what if I plug some numbers in here for x? I wonder what will happen. Well, let's just see. Let's take a 0, and we're going to plug that in for x. So I'm going to take that 0 and put it right here where my x variable is. So 0 squared would be 0. Let's try a 1 as our input. So I'm going to take that 1, put it in here for the x. 1 squared is 1. Let's try a 2. Put the 2 in for the x. 2 squared, that would be 4. Let's try a 3. Take the 3, put it in for x. 3 squared, that would be 9. Let's try some negative numbers. What will happen if we put a negative 1 in here? So when you take a negative and you put it in for this x here, then that negative 1 is going to get multiplied by itself. So you're asking yourself, what is negative 1 times negative 1? Well, the two negatives would turn to a positive, so that will be a positive 1. If you take a negative 2 and square that, well, negative 2 times negative 2 will turn out to be a positive 4. When you put a negative 3 in for x, you're going to get a positive 9. Okay, so we see something happening here. So let's go ahead and graph that. So you have some graph paper, so you can cut a little piece of it. And I'm going to draw an x and y axis on here. Now, I know that I'm going to need way more room above the x-axis for this one, so I'm going to put my x-axis way down low there. So let me just go ahead and plot some points here. There's 0, 0, 1, 1. 2, 4. You can pause this video if I'm going too fast. 1, 2, 3, 8, 9. Negative 1, 1. Negative 2, 4. Negative 3, 9. Now, I stopped making my table. That doesn't mean that we have stopped having values that we could graph, though. I could put in a 4, or a negative 4, or 5. I could put in 100 if I wanted for x. We'll talk about that all in a minute here, but I can see my curve developing. So I'm going to get this sketched in here. So you'll see that parabola shape. In fact, do you remember when you had me in 8th grade, if you had me in 8th grade, that we played Simon Says, and when you saw an x squared, you had to like, whew, do something like that. So we'll talk about that too in a minute. So there's our parent function. That is what the graph of y equals x squared looks like. So parabolas have some important features to them. So let's label some features here. This is the vertex. I'll show you another one that will have different x and y intercepts. So this one is not a good one to label those on. There's also always symmetry in these. So let me use a different color here. This is going to save you work when you notice this about parabolas. So who doesn't like to have a little bit less work to do on something? We should work smarter, not harder when possible. So parabolas will always have symmetry to them. There will always be a line that you could take them and fold them in half, like the two wings of a butterfly, fold them in half, and the two sides of the parabola will match each other. The reason that's helpful is if you know where there's a point on, say, the right side, then you can just mirror that on the left side. If you know a point on the right, you can mirror it on the left. Or if you know a point on the left, you can mirror it on the right. So it cuts down your workload. You can get those points faster because it's like you can find 2 for every one set of values that you plug in. So we just have to know where that line of symmetry is. And it will always be on the line where the vertex is. The vertex will always be either the lowest point or the highest point on your parabola. We need to graph more than just that basic parent function though. We want to graph some other types of parabolas. So let me write standard form first, and then I'll give you another equation to graph here. So standard form for a quadratic will look like this for the function. It'll be y equals ax squared plus bx plus c. Now when you actually have an equation, we're going to have numbers in here for the a and the b and the c. Those are, we just use them to stand for the a is the coefficient in front of the x squared, the b is the coefficient in front of the x, and the c is the constant that's on the end of the equation. Doesn't have to be on the end, but it's the constant. It just makes life easier to give those letters because it would get really old if you had to always say the coefficient in front of the x squared. It's much easier just to say a. So that's why we do that, okay? So let's use, as an example, let's use y equals x squared minus 6x plus 5. Okay, as our example. So I'll put example off here to the side. So let's see if we can identify what a and b and c would be. Well, okay, so a is the coefficient in front of the x squared. If I look down here, well, what is the understood coefficient? If you just have an x squared, but you don't specify how many x squareds you have, yeah, that's a coefficient of 1, because multiplying by 1 there doesn't change the value of it. So in this case, we have an a value of 1, so that's our a. The b value is the coefficient that's in front of the x. So in this case, that would be your -6. Notice I'm saying -6 because that sign's going to go with it. So our b value here is -6. And the constant that we have in this case is the 5. So we've identified what the coefficients are in standard form. So a couple of things about parabolas that you learned in the past, but you might have forgotten. One is, if you want to find where that fold line is, that axis of symmetry, it is always located at this formula. Axis of symmetry it is located at the line x equals -b over 2a. Now that is a helpful formula, so I'm going to make that stand out a little bit here in our notes. Oh, my red pen's kind of dying. So let's see if we can find the axis of symmetry for this equation now that we know what a and b and c are. So I need, I better move this up, x equals, so there's a negative sign in the formula, so I'm going to write down that negative sign. So here's the negative, and here's the negative. I'm bringing that down. Now I need to know what b is. Well, if I look over here on the left, our b value is a -6. All over 2 times, and then our a value here is a 1. So now it looks a little bit weird on the top with the double negative, so I would take that and change it to adding the opposite. So I have 6 over 2, which equals 3. So x equals 3 is where the axis of symmetry is going to be for this equation. So we're going to graph that. Let's see if I can keep this on here. Hopefully my picture isn't covering that up. I don't know. So let's see if I can get a little sketch going here. Okay, I'm going to have to move that out of the way for just a second. I'll move it back down. So x equals 3. I'm going to do this in a different color. We'll do this in purple. X equals 3. Remember your x-axis goes across, so I'm going to go 1, 2, 3. So here's where x equals 3. So I'm going to make a dotted line here. This is the line where x equals 3. So my parabola is going to somehow fold around that line. I don't know where it will begin on that line though, so I need to find where the vertex is. Well, luckily, since we have found the axis of symmetry is at x equals 3, that is half of the battle in finding your vertex as well. So the vertex is the point that's either going to be the minimum or the maximum of your parabola. So it will be the minimum or maximum of the parabola. And it will be an ordered pair. So we'll need an x value and a y value for it. And the x value is going to match this axis of symmetry. So once you have found that, you know the x value of your vertex. So I'm going to put that we use negative b over 2a here. And for this example, this is a 3. So I know that that vertex is somewhere on that purple dotted line. I just don't know where yet. So if I know the x value is 3, and I have the equation right here, y equals 1x squared minus 6x plus 5, what we're going to do is take that x value and plug it in. Oops. If I don't move, my lights shut off. It's very annoying. So anyway, this 3, I'm going to take that and plug it into the equation to find y. So I'm going to label this plug into equation to find y. Okay, so I'm going to take that 3 and we're gonna plug it in here for x. So the 3 is going to go up here. I'll do this in another color so you can see it. So y equals 1. I'm going to replace this x with a 3. Bring down the squared. Minus 6 times, here's another x, so I got to put 3 there again, plus 5. So now I just need to evaluate this. So I'll start with the exponent. 3 squared, that would be 9. Multiply that by 1, we're still at 9. So you have 9 minus, this multiplication here gives us 18. And I'll bring down the plus 5. So 9 minus 18, we're talking negative 9. And then I add 5 to that, and we'll be at negative 4. So the y value, so I'll put equals negative 4. So I'm going to put that right here. That is the y value of my vertex. So now I need to graph that. Oh, and it looks like I didn't make my graph quite big enough. It's okay though. So I'm going to go 1, 2, 3 over, and then 1, 2, 3, 4 down. So I'm just a little bit off my page. It's fine. So that gives me the vertex. I know it's on that purple line, just a little bit below since I ran out of space. No big deal. And this is going to have a shape like this, but we haven't talked about when it is going to smile and when it's going to frown. So that will come from your A value. If your A value is positive, it's going to smile like this, face up. If it's negative, it's going to face down like this. That should remind you about what we talked about with transformations. How transformations, if you have a negative A value, it flips it upside down. So that's what's happening here. Or well, if the A was negative. We do not have a negative A. So this one is going to smile, okay? It's going to face up. So I just need to find a couple of more points here so I know what this is going to look like. So I already know the vertex is at 3, negative 4. So that's the vertex. So that's good. So what I want to do is go just a little bit on either side of the vertex. So let's try an x value of 2. So I'm going to take that 2 and I'm going to plug it into my equation here for my x. So 2 squared, that would be 4. Multiplied by 1, I'm still at 4. Take the 2 and plug it in here for this x. That would be negative 12. So I have 4 minus 12, we're at negative 8. Add 5, we'd be at negative 3. So that value on my graph would be x is 2 and y is down 3. Okay, so right here. Now here's where the symmetry idea comes in. If there's a point 1 step away from the line of symmetry on the left, I can mirror that on the right. I don't have to do more math to find it. I can just use the fact that it's going to be symmetric. So I'm going to plug a 1 in for x. So if I put a 1 in, oops, can't see that, can you? I'm going to put a 1 in right here for x. So 1 squared would be 1. Multiplied by 1, it's still 1. If I put that 1 here, 6 times 1 is 6. So 1 minus 6, I'm at negative 5. Add 5, I'd be at 0. So at 1, 0, it's right here. So now I can use the symmetry idea. See how that point is 2 steps away from that line of symmetry? I'm going to mirror that directly on the other side of it. So let's do one more point just for good measure. I'm going to plug a 0 in for the x. 0 is nice and easy to plug in. So 0 squared is 0. 0 times 6 is 0. Plus 5, that would be positive 5. So 1, 2, 3, 4, 5. Here we go. And I can mirror that on the other side. And I would say this is a pretty good amount of information to sketch. Here we go. All right, so let's talk about the domain and range and end behavior and things like that on this parabola that we're looking at right here. So the domain on this, domain has to do with what? Your x's or your y's? Yeah, it has to do with your x's. So the domain here would be the x value. So that goes left and right. How far to the left is this going to go and how far to the right? Well, it's going to keep going forever. I could keep plugging in different x values and you could keep doing the math and getting answers for them. So the domain here would be all real numbers. So if I use interval notation, that would be from negative infinity to positive infinity. That's the domain. Now what about the range on this particular parabola? So the range is how high it goes and how low it goes. Okay, so when we name it as an interval, we always go, oops, I messed up a little bit. I'll tell you why in a minute. We always go low to high. So how low does this go? Well, that lowest point is at the vertex. And remember, range is the y's. So how low does that vertex go? Well, it goes to negative 4. Now here's where I messed up. I put the round parentheses, and that parabola actually can reach negative 4, so that needs a square one on that end. So that shows that the negative 4 value is included there. So that's how low the parabola goes. Now how high does it go? Well, it goes up forever because you see your infinity signs there, or your arrows. So I'm going to put an infinity sign. So that's the range on that. What about end behavior? So let's talk about as we go to the left. To say left, we say as x approaches negative infinity. That's the fancy way of saying left. What do your y's do as you're heading left? Well, they go up. So the fancy way of saying up is you say that y's approach positive infinity. So that's the left end. The fancy way of saying the right end is saying as x approaches positive infinity. That means you're heading right. So as I head to the right, what happens to my y's? Well, they also go up. So y's approach positive infinity on both ends. You can see the arrows go up on both ends. So that makes sense for that. Let's see, what else do we need to talk about? Oh, I said I would label some more things here. So let's see here. Let me switch colors. So we have our vertex. Often there's important stuff that happens at the vertex when you have story problems involving quadratics. Quadratics show up a lot in business if you want to look at minimizing cost or maximizing profit or things like that, there's often a parabola that will emerge when you graph things. So that vertex often matters a whole lot for that reason. Here is your y-intercept. It's where it hits the y-axis. And parabolas can have two x-intercepts. And we'll talk about, do they have to have two? Is it possible to have more than that, less than that? So these are your x-intercepts. I'm going to put an arrow way over here, I think, so I have some room to write. So these are your x-intercepts. We also refer to these as the roots and the solutions of the quadratic equation. So those are all code words, okay? Those are all referring to the x-intercept. So I could say, solve it, find me the roots, find me the x-intercepts. They all are saying, well, where's that happen at? Right there. Personally, I'm really proud of mathematicians for thinking of the word roots here, because like we're really normally pretty boring about naming stuff. We're like, where it intersects the y-axis, y-intercept, like not creative names. But roots, okay, so here's what you want to look at. Look at the x-axis is like the dirt line, like ground, okay, so this is like below ground down here, and this is like above ground up here. And so the parabola right here would be the transition between like the flowers growing above ground, and then down here would be the root system. So it's like where the roots start. So isn't that like pretty and poetic? I'm so proud of us. So you can call them roots if you want to be like artistic, an artistic mathematician. Let's see, what else do we need to talk about? Oh yeah, I didn't point out that there's a really cool pattern that emerges on the parent function. So let me look, let's see, let's go like this. So I want to look at the spacing that you're going to see here. I want to look at the spacing between the values. How far is it from 0 to 1? Well, that's going up 1. How far is it from 1 to 4? Oh, it's not up 1, is it? It's going up 3. This is not linear. That's why it's curving. Let's see what the next one does. How far is it from 4 to 9? Well, it goes up 5 to get from 4 to 9. Now, I didn't put 4 next in my x column. I wonder what would happen if I did. What if I put a 4 here in my x column? What's 4 squared? Well, 4 squared would be 16. So how big of a jump is it to get from 9 to 16? Oh, it adds 7. Now, before I figure out the next one, can you figure out what the next jump is going to be? Yep, it's going to go up 9. So that's an interesting pattern. We'll come back to that at some point. I just want to show you that right now. Okay, so the next thing I need to talk about is solving quadratic equations, because that's what the title of this section is. So we're talking about graphing the parabolas. What does that have to do with solving them? So let's say we are going to solve how about y equals negative x squared plus 4x plus 5. We're going to solve that. So, oh, I just said that wrong. Oh my goodness. Okay. There's an equation that we can solve. Sorry. The related function would be y equals negative x squared plus 4x plus 5. Functions have y's and x's. Equations just typically have one variable. So this is an equation in x's. It's not really a hard and fast rule, but that's how I'm going to differentiate today on this. So if I want to solve this, solve is going to be code word for find the roots, or you could also say find the x-intercepts. And you know other ways of solving quadratics besides graphing, but today what we're talking about is how can I use the graph to solve or find the x-intercepts or the roots, whatever words you want to use there. So that's what we're going to do for this. So let's first of all find the vertex, or find the axis of symmetry. So what is that formula for the axis of symmetry? So you're going to want to know this, okay? So this is where you use x equals negative b over 2a. So from our equation here, what would our b value be? Remember, they go in order. A is what's in front of the x squared, b is what's in front of the x, and c stands for constant. Yeah, so your b value would be the 4 here. So I'm going to plug that in. So the negative sign is here, so I'm bringing that down. Now I need the b, which is a 4, all over 2 times a. So 2 times, now the a value, I just see a negative sign, so that means we're talking -1. So I'm going to put a -1 there. So I have -4 over -2, which comes out to 2. So x equals 2 is where my axis of symmetry is. Oh, I need another piece. So we know that the axis of symmetry is going to be where x equals 2. So let's see, I'm going to get my x and y axis on here. Okay, so x equals 2 is, I'm going to do a purple dotted line. 1, 2. So here's where the fold is going to be on my parabola. So let's find some values. I need to know where that vertex is. Well, I know the x value of the vertex is at 2 because that axis of symmetry formula gives you the x coordinate of that. So now I need to take that 2 and plug it into my equation. So I'm going to take it up here and plug it into our equation. So 2, the squaring happens here before the negative sign. So 2 squared is 4, then there's a negative on the front of that. So -4, take the 2 and plug it in for this x, so that would be 8. So -4 plus 8, we're at +4. Add 5 to that, we're at 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I have to go 1 space above to get to that. Okay, so that's where my vertex is. I can tell that this one's going to face down. This is going to be a frown. How do I know that? Well, if I look at my a, my coefficient in front of my x squared, it's a negative, and that's going to make it frown. So I know it's going to go down from here. So let's get some other points. I'm going to put a 1 in for my x, put a 1 in here for x. So 1 squared would be 1. There's a negative sign in front of that, so we're at -1. Put the 1 in here as well. So 4 times 1 is 4. -1 plus 4, we're at 3. Add 5 to that, we'd be at 8. So that would be right here. I'm going to mirror that on the other side. Let's plug a 0 in for x. Put a 0 in here. That would be 0 plus 0 plus 5. So 1, 2, 3, 4, 5. Here we go. And I'll mirror that on the other side. Not handy, you can get half of them done by no work. Let's plug a -1 in for x. So now when I put the -1 in, that -1 is getting squared. So that's going to be a +1. But then there's another negative sign, so it turns back negative. That's -1 overall. 4 times -1 would be -4. So I would be at, what did I say? So -1 plus -4 would be -5. Add 5, I'd be at 0. So -1, 0, and then I'll mirror that on the other side. So here's where my parabola is going to go. Ta-da! So if I'm looking for the solutions of this, also known as the roots, also known as the x-intercepts, here they are. They are where the x value is -1 and where the x value is 3. Those are the 2 roots. So x equals -1 and x equals 3 are the 2 roots here. So on your assignment today, you are going to be graphing some, and I'll make another video to explain that part, I think, separate from this one. So That's everything. So remember, Jesus loves you, and so do I. So do your math.